You already know what a light year is. You've heard the term hundreds of times. It sounds technical, maybe even scientific, but not particularly mysterious. It's a unit of distance, a way of measuring how far away things are in space. Simple enough. But here's what most people don't realize. A light year isn't just a number with a lot of zeros attached to it. It isn't simply a longer version of a mile or a kilometer. It's something fundamentally different. It's a unit that exists because our normal ways of understanding distance completely fail when applied to the universe. It's a measurement born from the collapse of human intuition. When you truly understand what a light year represents, when you feel the weight of what it actually means, something shifts. The universe doesn't just become bigger in your mind, it becomes older, slower, more isolating, and strangely, more knowable at the same time. Because a light year isn't really about distance at all. It's about time. It's about separation. It's about the fundamental nature of reality itself. This isn't a lesson in astronomy. It's an exploration of what happens when you try to measure something so vast that the act of measuring it changes what you're measuring. It's about understanding why far stops meaning what you think it means the moment you leave Earth behind. And it's about recognizing that every time you look up at the night sky, you're not seeing distance, you're seeing history. Let's begin where all understanding begins, with something close, something familiar, something you can touch. Think about your morning drive to work. Maybe it's 15 miles, maybe 30. You know exactly how long it takes because you've done it hundreds of times. You know which lights slow you down, which routes save 3 minutes, where traffic builds up on Tuesdays. Distance, in this context, is something you understand completely. It's measured in time behind a steering wheel, in songs on the radio, in the fuel gauge dropping a quarter inch. Now imagine you decided to walk that same distance instead. The drive that takes 25 minutes becomes a 6-hour journey. Same road, same destination. But the experience transforms entirely. You notice things you've never seen from the car, side streets, small businesses tucked between larger buildings, the way the elevation changes gradually, almost imperceptibly over miles. Walking forces you to experience distance as effort, as duration, as a physical relationship between your body and the ground beneath it. This is how humans naturally measure distance, through movement, through time, through the lived experience of crossing from one point to another. We don't think in abstract units. We think in minutes walked, hours driven, days travelled. 100 miles feels different depending on whether you're in a car, on a bicycle, or moving on foot. The number stays the same, but its meaning shifts based on how you experience it. Consider a cross-country drive, Los Angeles to New York, roughly 2,800 miles. In a car, driving 8 hours a day, it takes about 4.5 days. You watch the landscape change through your windshield. Desert becomes plains. Plains become forests. Mountains rise and fall. You stop for gas, for food, for sleep. The distance becomes a narrative, a sequence of experiences stitched together by asphalt and time. You can tell someone about this journey and they understand it immediately because they know what a day feels like. They know what it means to drive for hours. The scale is large but entirely graspable. Even if you've never made that specific trip, you can construct it in your mind from smaller journeys you have made. You know what 200 miles feels like, so you can imagine doing that 14 times. You know what one 8-hour day of driving does to your body, the stiffness in your back, the fatigue in your eyes, so you can multiply that feeling by 4 or 5. The distance builds itself in your imagination through repetition of known experiences. But even this journey, this multi-day expedition across an entire continent, exists completely within the scale of human understanding. You can visualize it. You can plan for it. You know what it means to cover 2,800 miles because you know what it means to cover 1 mile, and you can multiply that experience, that effort, that duration, by a number that still feels manageable. 2,800 is large, but it's not incomprehensible. It's just many human-sized pieces arranged in sequence. Now go further. Imagine walking around the entire Earth at the equator. The circumference is roughly 25,000 miles. If you walked 8 hours a day at a steady 3 miles per hour, it would take you about 3.5 years. No rest days. No oceans to cross somehow. Just continuous walking. This begins to exceed casual imagination, but it's still grounded in something understandable. People have spent years walking long distances. Pilgrims, explorers, migrants crossing continents over generations. The scale is enormous. but it's built from human-sized steps, human-length days, human-span years. You could, in theory, do this. It would consume a significant portion of your life, but it wouldn't consume all of it. You could begin this journey at 25 and finish it before 30. You'd be a different person by the end, shaped by years of continuous movement, but you'd still be you. The same consciousness that started the walk would complete it. This is important. It means the distance, however vast, remains within the boundary of a single human experience. One life, one continuous thread of awareness moving through space. Every one of these distances, from your morning commute to a walk around the world, shares something fundamental. They can be experienced. They can be crossed. They exist within the framework of human life, human effort, human time. Whether you're driving to work or walking across a continent, you're moving through space in a way that makes sense to your body and your mind. You leave one place, you arrive at another. The journey has a beginning and an end, and you exist continuously between those 2 points. The distance is real because you can traverse it. It's knowable because you can break it down into steps, breaths, heartbeats. This is the foundation of how we understand distance. It's tangible, personal, lived, and it works perfectly well for everything humans encountered for most of our history. Your village to the next village, your city to the coast, one side of your country to the other. Distance was always something you could traverse, even if it took months or years. It was always something that could be broken down into manageable pieces into the rhythm of human movement and human time. Even when we built machines that moved faster than our bodies, the logic stayed the same. We just compressed the time. A horse covers more ground than walking. A car covers more ground than a horse. A train more than a car. An airplane more than a train. But the principle never changed. You're still moving through space sequentially, experiencing the journey as duration, arriving at the other end after a measurable, understandable period of time has passed. When the first commercial flights crossed the Atlantic, the journey that once took weeks on a ship collapsed into hours. People marveled at this compression of distance, this acceleration of experience. New York to London in 7 hours felt miraculous, but it was still the same fundamental type of distance. You boarded a plane in one place, you experienced several hours of travel, and you disembarked in another place. The distance was crossed, the journey was completed. You moved through every inch of space between the 2 points, even if you moved through it very quickly. But there's a problem with this system. It only works when the distances involved match the scale of human experience, even expanded human experience, even accelerated human experience. It only works when you can imagine crossing them, even hypothetically, even with the fastest vehicles we can build. It only works when time and distance stay coupled in a way that feels intuitive, where more distance simply means more time, and less time simply means faster movement. And the moment you step outside that scale, the moment you try to apply this same logic to anything beyond Earth, everything breaks down. Not gradually, not in a way that gives you time to adjust. It breaks down immediately and completely. The distances don't just become larger, they become different. They stop cooperating with human intuition entirely. They refuse to be understood through the framework of travel, of crossing, of movement from here to there. You can't walk to the moon. You can't drive to the sun. You can't take a multi-year journey to another star, not even a multi-century journey. Not even a journey that spans 1,000 human lifetimes placed end to end. The distances are too vast. The time required exceeds human lifetimes by factors so extreme they stop meaning anything at all. 1,000,000 years and 1,000,000,000 years both feel like forever to a creature that lives for 70 or 80 years. The numbers stop attaching to experience, and this is where the problem begins. Because the universe doesn't care about human-scale experience, it doesn't offer distances that fit neatly into our intuition. It operates on scales that make everything we know about far feel inadequate, childish, almost meaningless. A cross-country drive is not preparation for understanding cosmic distance. A walk around the Earth is not a stepping stone to comprehending the space between stars. They're not even on the same spectrum, they're different categories of existence entirely. So we had to find something else, something that could bridge the gap between what we can experience and what actually exists out there. Something that could turn incomprehensible distances into something we could at least name, even if we couldn't truly feel them, even if we couldn't cross them, even if we couldn't break them down into human-sized pieces. We needed a new ruler, a new way of thinking about distance that didn't depend on human bodies moving through space, that didn't depend on vehicles or time or effort or any of the familiar anchors we'd always used. And the answer was already travelling all around us, constantly, silently, faster than anything else in the universe. Light moves fast, you already know this, but knowing it as a fact and understanding what it actually means are not the same thing. When someone tells you that light travels at roughly 186,000 miles per second, the number lands in your mind as information, but it doesn't connect to anything real. You have no experience travelling at 186,000 miles per second. You have no reference point for what that speed feels like, what it looks like, what it does to distance. So let's start smaller. Start with something you can actually visualize. Imagine you're standing in an open field at night, and someone a mile away turns on a flashlight pointed directly at you. The light from that flashlight reaches your eyes essentially instantaneously. There's no perceptible delay. The moment the switch flips, you see the light. 1 mile at 186,000 miles per second is so fast that it might as well be instant. Your brain cannot detect the time that passes between the light leaving the flashlight and entering your eye. Now imagine that person is 10 miles away. Same result, 100 miles away, still instant. The light crosses that distance in a tiny fraction of a second, far less time than your nervous system needs to register anything at all. For all practical human purposes, light at these distances doesn't travel, it just appears. This is how we experience light in our everyday lives. We flip a switch and the room illuminates. We don't wait for the light, it's just there. This creates a fundamental misconception about what light actually is. We think of it as instant because that's how we experience it. We build our entire understanding of seeing, of vision, of visual experience around the idea that light simply exists wherever we look, that it's a static thing rather than a moving thing. But light is always moving, always travelling. It just moves so fast at human scales that the movement becomes invisible. Consider a lightning strike. You see the flash before you hear the thunder, sometimes by several seconds. This happens because light travels roughly 1,000,000 times faster than sound. The sound of the thunder, moving at about 767 miles per hour through air, takes time to reach you. Measurable time. Time you can count. If the lightning is a mile away, the thunder takes about 5 seconds to arrive. You can feel that delay. You can perceive it. It creates a gap between seeing and hearing that your mind easily registers. But the light from that same lightning strike reaches you in about 5 microseconds. 5 millionths of a second. You cannot perceive this. You cannot count it. You cannot feel it as a delay. To your senses, the light is instantaneous, and yet it did travel. It did cross that distance. It just did so at a speed that makes the journey invisible to human perception. This is the first hint that light operates on a scale fundamentally disconnected from human experience. Now let's try to make that speed more concrete. If you could somehow travel at the speed of light, you could circle the Earth's equator about 7.5 times in 1 second. Not 1 hour, not 1 minute, 1 second. Imagine watching the sun rise and set 7 times, watching the continents blur past, watching the oceans become streaks of blue, all in the time it takes to say the word one. This is not a speed that human bodies were built to comprehend. This is not a speed that evolution prepared us for. Or think about it this way. The distance from New York to Los Angeles is roughly 2,800 miles. At the speed of light, you would cross that entire continent in about 15 milliseconds. Less than 2/100ths of a second. Faster than you can blink. Faster than a single frame of video. The journey that takes 4.5 days by car, that takes about 5 hours by airplane, would be over before your brain could register that it had begun. This is where we start to see the strangeness of light as a measuring tool. Because 186,000 miles per second is not just fast. It's fast in a way that breaks our intuitive connection between speed and time and distance. When something moves at normal speeds, speeds we can relate to, there's a clear relationship. Double the speed, half the time. Simple, understandable. But when something moves at the speed of light, time almost stops mattering at human scales. Distances that seem vast to us become trivial. And yet, here's what's important. Even at this absurd, incomprehensible speed, even at the absolute speed limit of the universe, even moving faster than anything with mass can ever move, light still takes time to travel. It's not actually instantaneous. It just seems that way to us because we exist at such a small scale. The instantness is an illusion created by the mismatch between light's speed and our perception, and this illusion only works here, on Earth, at the distances we normally deal with. The moment you leave Earth, the illusion starts to crack. Not because light slows down. Light never slows down in a vacuum. It always moves at exactly the same speed, always 186,000 miles per second, constant and unchanging. But the distances change. They grow. They expand beyond the range where light's travel time can hide from human perception. And when that happens, when the distances become large enough, something strange occurs. Light stops being instantaneous. It starts having a measurable journey. It starts taking time, real time, time you can count and feel and observe. And when light, the fastest thing in the universe, starts taking noticeable time to travel, you begin to understand just how vast space actually is. Because if light is slow, if light has to work to cross a distance, if light takes seconds or minutes or hours or years to make a journey, then that distance has exceeded everything in human experience. This is the key insight. Light is our benchmark, our reference point. The fastest possible speed becomes the baseline for measuring cosmic distance, not because we chose it arbitrarily, but because nothing else works. Our cars are too slow, our rockets are too slow. Our fastest spacecraft, the ones we've sent to the outer solar system and beyond, are so slow compared to light that using them as a reference makes the universe seem even more impossibly vast. So we use light. We use the one thing that moves at the maximum possible speed, and we watch how long it takes to cover cosmic distances. And what we discover is that even light, even at 186,000 miles per second, even moving at a speed that makes it effectively instantaneous across the entire surface of Earth, struggles against the distances of space. Even light takes time. Even light has to travel. Even light creates delays that we can measure and observe and feel, and those delays tell us everything. They tell us how far away things really are. They tell us how isolated we are. They tell us that the universe is not just big, but big in a way that defeats even the fastest form of travel that physics allows. When you understand that light itself is not fast enough to make the universe feel small, you start to understand what cosmic distance actually means. Let's watch what happens when light leaves Earth and travels outward. Let's follow it and see where the illusion of instantaneous travel finally breaks down completely. Let's find the point where even light speed stops being enough. The moon is close, at least that's what we tell ourselves. It's the closest celestial body to Earth. It's right there in the sky, visible on most clear nights, close enough that we can see its features with our naked eyes. Close enough that we sent people there in the 1960s and 70s. Close enough that the journey, while difficult and dangerous, took only 3 days. By cosmic standards, by any reasonable measure of space distance, the moon is practically touching us. The average distance from Earth to the moon is about 238,855 miles. This is roughly the distance you'd cover if you drove around Earth's equator 10 times. A long distance by human standards, certainly, but not incomprehensible, not beyond imagination. If you could somehow build a road to the moon and drive there at highway speeds, it would take you about 5 months of continuous driving. Long, yes. Tedious, absolutely, but possible to conceive. You could imagine yourself making that journey. Now watch what happens when light makes the same journey. Light, travelling at 186,000 miles per second, takes about 1.28 seconds to travel from the moon to Earth. A little over 1 second. This is the first time in our exploration where light's travel time becomes noticeable. Not by much, not in a way that matters in most circumstances, but it's there, measurable, real. When you look up at the moon on a clear night, you're not seeing the moon as it is right now. You're seeing it as it was 1.28 seconds ago. This sounds trivial. 1 second is nothing. 1 second is a heartbeat. 1 second is barely enough time to form a conscious thought. But this is the moment where something fundamental changes. This is where distance stops being just distance and starts being time. This is where the separation between objects in space reveals itself as something stranger than mere physical gap. The Apollo astronauts who walked on the moon experienced this delay in a very direct way. When they communicated with mission control in Houston, there was a pause. They would say something, and then there would be silence. About 2.6 seconds of silence. Then the response would come, another 2.6 seconds later, their reply. This wasn't a technological limitation. This wasn't slow equipment or processing delays. This was light itself, carrying their voices as radio waves, taking time to cross the distance. Radio waves are light, different frequency, same fundamental thing, travelling at the same speed. So when an astronaut on the moon spoke into their radio, those words became electromagnetic waves that had to physically travel the 238,855 miles back to Earth, 1.28 seconds to get there. Then the response from Houston had to make the return journey, another 1.28 seconds, round trip, 2.6 seconds of unavoidable delay, built into the fabric of reality itself. You can hear this in the recordings of the Apollo missions. The conversations have a strange rhythm, a pause after every statement, a gap that feels slightly too long, slightly unnatural. The astronauts in mission control adapted to it, learned to wait for it, built it into how they communicated. But it was always there, an artifact of distance, a reminder that even though the moon looked close enough to touch in the sky, even though humans had successfully travelled there, there was still a barrier that couldn't be crossed, a delay that couldn't be eliminated. This is the first place where light speed stops being adequate. At Earth-scale distances, light is effectively instant, but between Earth and the moon, light starts to lag. It starts to create temporal separation. You and the moon are not experiencing the same present moment. When you look at the moon, you see its past. When someone on the moon looks at Earth, they see our past. The two objects exist in slightly different timeframes, separated by the distance light has to travel. Think about what this means. If something happened on the moon right now, some event, some change, some occurrence, you wouldn't know about it for 1.28 seconds. Not because the information was being processed slowly, not because someone had to relay the news, but because the information itself, travelling at the maximum possible speed, takes that long to reach you. There is no way to know about it faster. No method, no technology, no trick of physics can overcome this. The delay is absolute. This creates something called the light cone, though we don't need to dwell on the terminology. The basic idea is simple. Information can only travel at the speed of light. Therefore, there's a boundary around every event in space, expanding outward at light speed, beyond which the event hasn't happened yet. Inside that boundary, the event is in the past. Outside, it's in the future. And that boundary takes time to expand. For the moon, it takes 1.28 seconds for that boundary to reach Earth. Now, 1.28 seconds doesn't seem meaningful. It doesn't feel like a real barrier. You can barely notice it in conversation. The Apollo astronauts worked around it without much difficulty. But here's what matters. This delay exists. It's small, but it's real. And if the moon, our closest neighbour, the only other world humans have ever stood on, is already far enough away that light has to work to reach it, what happens when we go farther? What happens when we look at something not 240,000 miles away, but millions of miles away? What happens when light has to travel not for 1 second, but for minutes? What happens when the delay stops being a minor inconvenience and starts being a fundamental barrier to any kind of real-time interaction? The moon gives us our first glimpse of this. It shows us that even at cosmic distances we consider close, even at distances we've physically crossed, light is not instant. Light takes time, and time creates separation. You start to see the problem. If we ever want to establish a permanent presence on the moon, if we want to build bases there, live there, work there, we'll have to accept this delay. Every conversation with Earth will have that gap. Every piece of information will be 1.28 seconds old when it arrives. Every emergency will have a built-in response lag. You can't have a real-time video call with someone on the moon. You can't coordinate activities that require instant communication. You're always operating on slightly outdated information. And this is just the moon. This is the beginning. This is the smallest version of the problem, because light doesn't just struggle with the moon. It struggles with everything beyond Earth, and the farther out you go, the more profound the struggle becomes. The delays grow from seconds to minutes to hours to days to years. And as those delays grow, the entire concept of now starts to dissolve. The present moment stops being shared. Distance becomes indistinguishable from time, and the universe reveals itself as not just vast in space, but vast in time, with every object existing in its own temporal island, separated from every other object by the speed of light. Let's go farther. Let's watch those delays grow. Let's find out what happens when light doesn't just take a second to travel, but takes minutes. Let's go to the center of our solar system and see what the sun can teach us about distance. The sun is 93 million miles away from Earth. We call this distance one astronomical unit, or AU, and we use it as a baseline for measuring distances within our solar system. It's a number we teach in elementary school. It appears in textbooks and planetarium shows. It's presented as a simple fact, a piece of basic astronomical knowledge. But like most cosmic distances, the number itself tells you almost nothing about what the distance actually means. 93 million miles. If you tried to drive to the sun at highway speeds at a steady 65 miles per hour, never stopping, never slowing down, it would take you about 163 years. That's longer than any human lifespan. Longer than the entire history of the United States as a country. You would need multiple generations of drivers, each one taking over from their predecessor, passing down the journey like an inheritance, just to cover the distance between Earth and the star that gives us light and warmth and life itself. But we're not measuring with cars anymore, we're measuring with light. And light, travelling at 186,000 miles per second, takes approximately 8 minutes and 20 seconds to travel from the sun to Earth. 8 minutes! That's less time than it takes to hard-boil an egg, less time than a typical commute to work, less time than an episode of most television shows. It seems short, manageable, almost trivial. But consider what those 8 minutes actually represent. When you step outside on a sunny day and feel warmth on your skin, you're feeling sunlight that left the sun's surface 8 minutes ago. The light touching you right now began its journey before you stepped outside, before you put on your shoes, before you decided to go for a walk. By the time you feel it, it's already old, already a piece of the past. The sun you see in the sky is not the sun as it exists in this moment. It's the sun as it existed 8 minutes ago. This might seem like a technical detail, an interesting bit of trivia. But think about what it means. If the sun exploded right now, if it suddenly ceased to exist in this exact moment, you wouldn't know for 8 minutes. The sky would still be bright. The warmth would still reach Earth. Birds would still sing. Plants would still photosynthesize. Everything would continue exactly as normal, because the light from the explosion, the information about the catastrophic change, would still be travelling toward us. The news would still be in transit, crossing those 93 million miles at the maximum possible speed. For 8 minutes and 20 seconds, Earth would orbit a star that no longer existed. We would live in a universe that had fundamentally changed while believing everything was normal. Our present moment and the sun's present moment would be completely disconnected, and there would be no way to bridge that gap, no way to know what was happening at the sun right now. No method, no technology, no advancement in physics could overcome the simple fact that information takes time to travel, and the sun is far enough away that the travel time matters. This is where the delay starts to become meaningful. The moon's 1.28 second lag was noticeable but minor. 8 minutes is different. 8 minutes is long enough that you can do things. You can make decisions, you can change your mind, you can have entire conversations. And throughout all of that, the light that will eventually reach you is still travelling, still crossing the void, carrying information about a sun that existed when those activities began. Astronauts on the moon dealt with a 2.6 second round-trip communication delay. Annoying, but workable. Now imagine trying to communicate with something near the sun. You send a message. 8 minutes later, it arrives. If there's an immediate response, it takes another 8 minutes to get back to you. Total round trip, 16 minutes and 40 seconds. Nearly 17 minutes between saying something and hearing a reply. This is no longer a conversation. This is an exchange of letters. You send a statement, you wait, you receive a response to something you said almost 20 minutes ago. Any sense of real-time interaction dissolves completely. And we're still inside our own solar system. We're still talking about our own star, the central body around which our planet orbits, the object that dominates our sky and our lives. If we're this isolated from the sun, if light takes this long to cross a distance we consider relatively close, what does that say about everything else? Let's push this further. Let's think about the sun not just as a source of light, but as a source of gravity. The sun's gravity holds Earth in orbit. It's what keeps us circling at a steady distance instead of flying off into interstellar space. But gravity, like light, doesn't act instantaneously across distance. gravity propagates at the speed of light. This means if the sun disappeared right now, Earth wouldn't just continue to orbit nothing for 8 minutes while waiting for the light to fade. Earth would continue to orbit nothing for 8 minutes while waiting for the gravitational change to reach us. For 8 minutes, we would be held in orbit by a gravitational field from a star that no longer existed. The curvature in space-time that keeps Earth moving in its elliptical path would still be there, propagating outward from where the sun used to be, not yet updated to reflect the new reality. Gravity is not a force that reaches across space instantly. It's information about mass and space-time, and like all information, it travels at light speed. So the sun's gravity right now is the sun's gravity from 8 minutes ago. This creates a strange situation. Everything we interact with from the sun is delayed. The light we see is 8 minutes old. The gravity we feel is 8 minutes old. If we could somehow measure the solar wind, the stream of charged particles flowing out from the sun, we'd find that it too takes time to reach us. We don't live in the same present moment as the sun. We live in the sun's past. Always. Constantly. By the time we experience anything from the sun, it's already history. Now think about the other planets. Mercury, the closest planet to the sun, orbits at about 36 million miles from our star. Light takes roughly 3.2 minutes to travel from the sun to Mercury. Venus, at 67 million miles, receives sunlight that's about 6 minutes old. Earth, as we've established, gets 8-minute-old sunlight. Mars, at 142 million miles on average, receives sunlight that's about 12.6 minutes old. Each planet exists in its own temporal relationship with the sun. Each one experiences the sun's present moment at a different time. If you could somehow observe all the planets simultaneously, see them all as they exist right now in this exact moment, you'd see each one illuminated by a different moment in the sun's past. Mercury would be showing you the sun from 3.2 minutes ago, Venus from 6 minutes ago, Earth from 8.3 minutes ago, Mars from 12.6 minutes ago. They're all orbiting the same star, but they're all experiencing different versions of it, each version separated from the others by the time it takes light to cross the intervening space. This is what light delay does. It fractures the concept of now across space. There is no universal present moment. There's only a collection of local present moments, each one isolated from the others by distance and the speed limit of information. The farther apart two objects are, the more disconnected their experience of time becomes. Not because time itself changes, but because the information about what's happening takes longer to travel. And here's the crucial part. This isn't a limitation of our technology. This isn't something we can engineer our way around. This is fundamental physics. Information cannot travel faster than light. Cause and effect cannot propagate faster than light. The universe has a speed limit, and that speed limit creates unavoidable delays whenever distance is involved. The sun is 93 million miles away, so we experience it with an 8-minute delay. Always, forever. No matter what we invent or discover, that delay will remain. This is what makes space isolating. Not just the physical distance, but the temporal distance. The delay. The lag between event and observation. When you're on Earth looking at the moon, you're looking 1.28 seconds into the past. When you're on Earth looking at the sun, you're looking 8 minutes into the past. And when you look at anything farther away, the past you're seeing gets deeper and deeper. Distance in space is always distance in time. The two are inseparable. So when we try to measure cosmic distances, when we try to understand how far away things really are, we're not just measuring space, we're measuring time. We're measuring how long information takes to travel. We're measuring the delay between something happening and us knowing about it. And light, the fastest thing that exists, becomes our ruler, because it shows us the minimum possible delay. If light takes 8 minutes to get here from the sun, nothing else can do it faster. 8 minutes is the best case scenario, the absolute minimum isolation distance. And we're still barely outside Earth's orbit. We haven't even left the inner solar system. We haven't approached the outer planets, where delays stretch from minutes into hours. We haven't considered the edge of the solar system, where light takes days to travel. And we certainly haven't begun to contemplate interstellar distances, where light takes years. The sun, at 8 minutes away, is just the beginning of understanding what cosmic distance means. It's the first real barrier, the first place where light speed becomes noticeably inadequate. Let's keep going outward. Let's see what happens when those minutes become hours and hours become days. Let's watch the solar system reveal just how empty it really is. Jupiter orbits the Sun at an average distance of about 484 million miles. This is roughly 5 times farther from the Sun than Earth is, or 5 astronomical units. Light from the Sun takes approximately 43 minutes to reach Jupiter. If you were standing on one of Jupiter's moons, looking up at the Sun in the sky, you'd be seeing it as it was 43 minutes ago. Not 8 minutes like on Earth. 43 minutes. The Sun you'd observe would have existed nearly 3/4 of an hour in the past before its light finally completed the journey to where you're standing. Now imagine you wanted to send a radio signal from Earth to a spacecraft orbiting Jupiter. Radio signals, like all electromagnetic radiation, travel at the speed of light. The distance between Earth and Jupiter varies depending on where both planets are in their orbits. At their closest approach, when they are on the same side of the Sun, they're about 365 million miles apart. At their farthest, when they're on opposite sides of the Sun, they're about 601 million miles apart. Let's use an average distance of about 484 million miles. A radio signal sent from Earth to Jupiter would take roughly 43 minutes to arrive. If the spacecraft responded immediately, that response would take another 43 minutes to return to Earth. Total round-trip communication time, 86 minutes, an hour and 26 minutes. This is no longer a delay you can work around with slight adjustments in conversation rhythm. This is a wall. A fundamental barrier to any kind of interactive communication. You cannot give real-time commands to a spacecraft at Jupiter. You cannot troubleshoot problems as they happen. You cannot have any form of back-and-forth dialogue. Every instruction you send is 43 minutes old by the time it arrives. Every piece of data you receive is 43 minutes old by the time you see it. If something goes wrong on the spacecraft, something that requires immediate human decision-making, those 43 minutes are built into the problem. The spacecraft is on its own during that time. It has to handle the situation autonomously or not at all, because no amount of human expertise on Earth can reach it faster than light allows. This is why spacecraft that travel to the outer solar system are designed with significant autonomous capabilities. The Galileo probe, which orbited Jupiter from 1995 to 2003, couldn't rely on Earth for quick decisions. The Juno spacecraft, currently studying Jupiter, operates largely on its own. Engineers on Earth send it commands, but those commands are planned well in advance, uploaded in batches, executed by the spacecraft's onboard systems according to predetermined schedules. The spacecraft has to be smart enough to handle unexpected situations because by the time Earth knows something went wrong, it's already been wrong for 43 minutes. Think about what this means for human exploration. If we ever send astronauts to Jupiter's moons, which some long-term space exploration plans consider, those astronauts will be more isolated from Earth than any humans have ever been. When the Apollo astronauts walked on the moon, they had a 2.6-second communication delay. Annoying, but manageable. They could still talk to mission control, still receive guidance, still feel connected to Earth in a meaningful way. Astronauts at Jupiter would have an 86-minute round-trip delay. They would send a message and then wait nearly an hour and a half before hearing any response. By the time mission control answers a question, the question might no longer be relevant. The situation might have evolved. The problem might have resolved itself or gotten worse. This is isolation on a scale humans have never experienced. It's not just physical distance, it's temporal disconnection. You and Earth are no longer sharing the same practical moment. Your now and their now are separated by a gap that cannot be closed. You can't call home when you're scared, you can't ask for immediate help when something breaks. You can't hear a familiar voice reassuring you in real time. Everything from Earth is old news by the time it reaches you. Everything you send to Earth is old news by the time they receive it. And Jupiter isn't even the farthest planet. Let's keep going. Saturn orbits at about 886 million miles from the Sun. Light takes roughly 80 minutes to travel from the Sun to Saturn. A round-trip radio signal between Earth and Saturn at average distance takes about 2 hours and 40 minutes. 2 hours and 40 minutes between question and answer. You could watch an entire movie in the time it takes to send a message to Saturn and receive a response. Uranus, at 1.8 billion miles from the Sun, receives sunlight that's about 2 hours and 40 minutes old. Round-trip communication with Earth, approximately 5 hours and 20 minutes. Neptune, the farthest planet in our solar system, orbits at about 2.8 billion miles from the Sun. Light takes roughly 4 hours and 10 minutes to get there. Round-trip communication, about 8 hours and 20 minutes, an entire workday. You could send a message to Neptune in the morning and receive a response after dinner. These aren't just numbers. These are real operational constraints that affect every spacecraft we've ever sent to the outer solar system. Voyager 2, which visited all 4 outer planets and is now in interstellar space beyond our solar system, operates with communication delays that currently exceed 22 hours one way. When engineers send a command to Voyager 2, they have to wait more than a day and a half to know if it worked. If something goes wrong, if the command causes an error, they won't know about it for 22 hours. Then they have to diagnose the problem, formulate a solution, and send new commands, which take another 22 hours to arrive. A simple troubleshooting session could easily span 3 or 4 days. The spacecraft has to be robust enough to survive its own mistakes during those delays. It has to have fallback systems, autonomous error handling, redundancies built into everything. Because Earth can't save it quickly, Earth is always watching the past, always responding to old information, always operating with a fundamental handicap imposed by the speed of light and the vastness of space. Now let's think about what this means for our understanding of the solar system itself. We think of the solar system as our local neighbourhood, our home region. The planets are our neighbours. We've sent spacecraft to all of them. We have photographs, data, measurements. We've mapped their surfaces, studied their atmospheres, analysed their compositions. In that sense, they feel known, accessible, part of our extended territory. But the light delays tell a different story. They tell us that even within our own solar system, even among the planets that orbit the same star we do, we are profoundly isolated. Neptune is not our neighbour in any meaningful sense. Neptune is 4 hours and 10 minutes away at the speed of light. That's not a neighbourhood. That's a separate world, existing in its own temporal bubble, so far removed from our present moment that real-time interaction is impossible. And here's what makes it worse. We've been measuring distances from the Sun, from the centre of the solar system outward, but what about distances between planets? What about the gaps that exist when you're not moving from the centre to the edge, but from one point on the edge to another? Earth and Neptune, when they are on opposite sides of the Sun, are separated by about 2.9 billion miles. Light takes approximately 4 hours and 22 minutes to cross that distance. If you were on Neptune and looked toward Earth with a powerful enough telescope, you wouldn't see Earth as it is now. You'd see Earth from 4 hours and 22 minutes ago. You'd see people going about their lives, but those people would have already finished what they're doing. They'd have moved on. They'd be doing something else entirely by the time you observed them. This is the strangeness of cosmic distance. It turns space into a kind of time machine. Not the science fiction kind, where you can travel backward and forward at will, but a more subtle kind. A kind where looking outward is automatically looking backward. Where every observation of anything distant is an observation of the past. Where the farther you look, the deeper into history you see. The planets in our solar system are all circling the same star, all bound by the same gravitational system, all part of the same orbital family. But they're not experiencing the same present. They're each locked in their own version of now, separated from each other by light travel time. When something happens on Earth, Neptune won't know about it for hours. When something happens on Neptune, Earth won't know about it for hours. The two worlds exist in parallel, sharing the same space but not the same time. And this is still just our solar system. This is still our immediate cosmic environment. We haven't left the Sun's gravitational influence. We haven't crossed into the space between stars. We're still, by any reasonable cosmic measure, at home, and yet already the distances are large enough that light struggles to cross them quickly. Already the delays are measured in hours. Already the isolation is profound. But there's more to the solar system than the planets. There are smaller objects, dwarf planets like Pluto, orbiting at about 3.7 billion miles from the Sun on average. Light takes approximately 5.5 hours to reach Pluto. There are comets in the Oort cloud, a vast spherical shell of icy objects that surrounds the solar system, extending perhaps 1 or 2 light years from the Sun. Objects at the inner edge of the Oort cloud might be a few trillion miles away. Light from the Sun takes months to reach them. Objects at the outer edge might be so far away that sunlight takes a year or more to arrive. These objects are still gravitationally bound to the Sun. They're still part of our solar system, but they exist in a version of the solar system where the Sun is no longer a bright disk in the sky. It's a point of light. Brighter than other stars, yes, but not dramatically so. And the light from that point takes so long to arrive that the sun those objects see is the sun from months or years in the past. They orbit a star that, from their perspective, exists in deep history. This is what our solar system actually is. Not a tight collection of planets orbiting relatively close to their star, but a vast region of space with enormous gaps between objects. Gaps so large that light takes hours or days or months to cross them. The distances within our solar system are already large enough to fragment time, to create isolation, to make real-time interaction impossible across much of its volume. And this is before we've even considered the truly vast distances. The distances between stars. The distances measured not in light hours or light days, but in light years. Let's cross that threshold. Let's leave the solar system entirely and see what happens when light has to travel for years instead of hours. In 1977, NASA launched two spacecraft called Voyager 1 and Voyager 2. Their primary mission was to explore the outer planets, to fly past Jupiter and Saturn, and, in Voyager 2's case, continue on to Uranus and Neptune. They completed those missions spectacularly, sending back the first close-up images of these distant worlds, revolutionizing our understanding of the outer solar system. But their journey didn't end there. After passing the planets, both spacecraft continued outward, moving away from the Sun, heading into the space between stars. They're still travelling now, decades later, still sending back data, still functioning despite being farther from Earth than any human-made object has ever been. Voyager 1 is currently about 15 billion miles from Earth. That distance increases by roughly 325 million miles every year as the spacecraft continues its outward journey at about 38,000 miles per hour. This is fast by human standards. It's about 50 times faster than a passenger jet. It's fast enough to cross the United States in less than 5 minutes, but compared to the speed of light, it's extraordinarily slow. Voyager 1 is travelling at roughly 0.006% of light speed. Not 6%, not even 0.6%, 0.006%. At this speed, light would lap Voyager 1 more than 17,000 times in a single second. If you could watch both light and Voyager 1 leave Earth simultaneously, the light would reach the Moon before Voyager 1 travelled 15 miles. The light would reach the Sun before Voyager 1 made it to Saturn. The light would reach the nearest star before Voyager 1 cleared the outer solar system. Light doesn't just move faster than Voyager 1, it exists in an entirely different category of motion. The comparison is almost meaningless because the scales are so different, and yet Voyager 1, even at this crawling pace relative to light, is the fastest spacecraft ever launched in terms of velocity relative to the Sun. It represents the best we've been able to do with rocket technology. It's been travelling for more than 45 years, and it's only just now entering what we might call interstellar space, the region between stars where the Sun's influence fades and gives way to the general galactic environment. 15 billion miles sounds enormous, and it is by any human measure, but it's barely the beginning of true cosmic distance. Let me put this in perspective. Voyager 1 is moving away from us at about 38,000 miles per hour. It's been doing this for over 4 decades, and if it were headed toward the nearest star system, Alpha Centauri, which is about 4.37 light years away, it would take approximately 73,000 years to get there. Not 73 years, 73,000 years. That's longer than all of recorded human history. That's longer than humans have had agriculture, cities, writing, civilization. Voyager 1 could travel for the entire span of human cultural development, from the first permanent settlements to the present day, and it still wouldn't arrive at the nearest star. This is the gap we're dealing with. This is what interstellar distance means. Our fastest spacecraft, travelling for timescales that dwarf human history, can barely begin to cross the space between our Sun and the next nearest star. And Alpha Centauri isn't even far by cosmic standards. It's our closest stellar neighbour, is right next door. If the Milky Way galaxy were a country, Alpha Centauri and the Sun would be in the same neighbourhood, practically sharing a fence line. And yet the distance between them is so vast that our best technology would take 73,000 years to cross it. Now compare this to light. Light travels from the Sun to Alpha Centauri in 4.37 years, not 73,000 years. 4 years and a few months. This is still a long time. This is still a distance that creates profound isolation, but it's comprehensible. It's within the span of human experience. You could be 4 years old when light leaves Alpha Centauri, and you'd only be 8 years old when that light reaches Earth. The same light that would witness your entire elementary school education, your adolescence, your early adulthood, and a significant portion of your career if it were making the journey on Voyager 1 would instead arrive before you finish 3rd grade. This comparison reveals something crucial about why we measure cosmic distances in light years rather than miles or kilometers. Miles don't help. Saying that Alpha Centauri is 25 trillion miles away doesn't make the distance more understandable, it just adds zeros. The number is too large to connect to anything in human experience. You can't visualize 25 trillion of anything. You can't break it down into familiar units. It's an abstraction that conveys magnitude without meaning. But saying Alpha Centauri is 4.37 light-years away tells you something immediate and concrete. It tells you that light, travelling at the fastest possible speed, takes 4.37 years to get there. It tells you that when you look at Alpha Centauri through a telescope, you're seeing it as it was 4.37 years ago. It tells you that if you wanted to send a message there, even at light speed, it would take 4.37 years to arrive, and any response would take another 4.37 years to return. Round-trip communication time, 8.74 years, nearly a decade between question and answer. This is why the light year works as a unit, not because it makes the distances smaller or easier to comprehend, but because it ties distance directly to time, and time is something we understand. We know what a year feels like. We know what 4 years feels like. We can imagine waiting 4.37 years for something. We can't imagine travelling 25 trillion miles, but we can imagine waiting for 4.37 years while light does the travelling for us. And this is the smallest interstellar distance we have. This is our nearest neighbour. Most stars are much, much farther away. The next nearest star after Alpha Centauri is Barnard's star at about 6 light-years. Then Wolf 359 at 7.8 light-years. Sirius, the brightest star in Earth's night sky, is 8.6 light-years away. These are all still within our immediate stellar neighbourhood. These are the stars that would be affected if something catastrophic happened to the Sun. These are the stars we might hope to reach someday if we develop faster spacecraft, and they're already separated from us by distances that light takes years to cross. Let's think about what this means for space exploration, for human exploration. Right now, the farthest any human has travelled from Earth is about 248,655 miles, the distance achieved by the Apollo 13 astronauts when they swung around the Moon. That's roughly 1 light second, 1 second at light speed. The Moon itself is about 1.28 light seconds away, and we've sent 12 humans there across 6 successful missions. Mars, at its closest approach to Earth, is about 3.1 light minutes away. We've never sent humans to Mars, but it's within the realm of possibility. The trip would take 6 to 9 months with current technology, and communication delays would be manageable if awkward. But the nearest star is 4.37 light-years away. Even if we could build a spacecraft that travelled at 1% of light speed, which would be an extraordinary achievement far beyond our current capabilities, the journey to Alpha Centauri would take 437 years, multiple human lifetimes, multiple generations. You would need a generational ship, a vessel large enough to support a complete society, where people are born, live their entire lives, and die without ever seeing the destination. Their children would continue the journey, and their children's children, and so on for centuries until finally, descendants so far removed from the original crew that they might not even speak the same language would arrive at a star system that their ancestors left Earth to reach. This is science fiction territory, but it illustrates the problem. Interstellar distances aren't just large. They're large in a way that makes conventional space travel absurd. You can't just build a faster rocket and solve the problem. You'd need to build a rocket so fast, so far beyond anything we can currently imagine, that it approaches significant fractions of light speed. And even then, even if you could travel at 10% of light speed, which would require energy and engineering breakthroughs we can't currently foresee, the journey to Alpha Centauri would still take 43 years, an entire human lifetime for a one-way trip to the nearest star. Light doesn't care about these problems. Light makes the journey in 4.37 years every time, with no fuel required, no life support, no complex engineering. Light just goes. It leaves the Sun and arrives at Alpha Centauri 4.37 years later. Simple, consistent, reliable, and this is why light becomes our measuring stick. Because if light, the fastest thing that can exist, takes years to cross interstellar distances, then those distances are fundamentally beyond human reach, using anything like our current understanding of travel. Voyager 1 will never reach another star, not in any meaningful time frame, not in the lifetime of human civilization as we know it. It will drift through interstellar space for tens of thousands of years, a tiny artifact of a species that briefly existed on a small planet orbiting an average star. The spacecraft might outlast humanity itself, might continue travelling long after Earth has become uninhabitable, long after the Sun has changed and expanded and consumed the inner planets. Voyager 1 could be the longest-lasting remnant of human existence, and it will never arrive anywhere. It will just travel. Forever. Slowly. Alone in the dark. This is what interstellar distance means. It means that even our fastest achievements, our most ambitious spacecraft, our greatest technological accomplishments are laughably inadequate for crossing the gaps between stars. It means that the only thing fast enough to make these journeys in reasonable timeframes is light itself. And even light takes years. Even light, travelling at the absolute cosmic speed limit, has to work to cross the space between one star and another. And we're still just talking about our immediate neighbourhood. We're still discussing the closest stars, the ones within a few light years. What happens when we expand our view? What happens when we look not at individual stars, but at the structure they form? What happens when we try to measure not the distance to our neighbour, but the distance across our entire stellar community? Proxima Centauri is the closest star to our Sun. Not Alpha Centauri itself, which is actually a binary system of two stars, but Proxima Centauri, a small red dwarf that orbits the Alpha Centauri pair at a great distance. Proxima is 4.24 light-years away. This makes it our nearest stellar neighbour by a small margin. The light you see from Proxima Centauri tonight left that star in 2021. The star you're observing no longer exists in that state. It has changed, moved, evolved, however slightly. By the time you see it, it's already history. 4.24 light-years. Let's ground that in something tangible. Imagine you could build a bridge to Proxima Centauri. An impossible bridge, obviously, but stay with the thought. If you started walking across this bridge at a steady pace of 3 miles per hour, 8 hours a day, it would take you approximately 306 million years to reach the other side. That's longer than dinosaurs have been extinct. That's longer than complex life has existed on Earth. You would need to walk continuously through the entire evolution of mammals, through the rise and fall of countless species, through ice ages and warm periods and mass extinctions, just to cross the distance between our Sun and the nearest other star. But we're not measuring with walking anymore. We're not even measuring with spacecraft. We're measuring with light, and even light takes 4.24 years to make this journey. This means something profound. It means that Proxima Centauri and our Sun do not share a present moment. They cannot. The information that would allow them to share a present moment, the light and electromagnetic radiation that carries information about what's happening now, takes 4.24 years to travel between them. They are separated not just by space, but by time itself. If Proxima Centauri has planets, which it does, at least 2 that we've detected, those planets exist in a version of the universe where Earth as it is right now doesn't exist yet. When someone on a planet orbiting Proxima Centauri looks at our Sun through a telescope powerful enough to see Earth, they're not seeing us as we are today. They're seeing us from 4.24 years ago. They're seeing 2021. They're watching events that, for us, have already concluded. Decisions that have already been made, moments that have already passed into memory. And we're doing the same thing to them. When we observe Proxima Centauri, we're seeing its past. The star we study is a star that existed 4.24 years ago. Anything that has happened there in the last 4.24 years is completely unknown to us, unknowable, hidden behind the light travel time. If a planet around Proxima Centauri exploded yesterday, we wouldn't know for more than 4 years. If an advanced civilization there decided to send us a message today, we wouldn't receive it until 2029. If they're sending us a message right now, it's still crossing the void, still travelling through empty space at light speed, still years away from arrival. This is the isolation of interstellar distance. It's not just that we can't travel there quickly, it's that we can't know what's happening there now. The concept of now breaks down completely. There is no now that includes both Earth and Proxima Centauri. There's only Earth's now and Proxima Centauri's now, separated by 4.24 years of light travel time, forever out of sync, forever unable to share the same present moment. Let's think about what this means for communication. If we detected a signal from Proxima Centauri tomorrow, if we received clear evidence of an intelligent civilization sending us a message, that message would have been transmitted 4.24 years ago. The civilization that sent it has already moved on. They've lived 4.24 more years since they pressed send. If we wanted to respond, our response would take another 4.24 years to reach them. They would receive our reply 8.48 years after they sent their original message, nearly a decade between question and answer. Any conversation would be impossibly slow. You would send a greeting and wait 8.48 years to know if it was received. You would ask a question and wait 8.48 years for the answer. By the time the response arrived, you might not even remember asking the question. You might have lost interest. You might have changed your mind about what you wanted to know. The person who asked the question and the person who received the answer would be separated by nearly a decade of life experience, enough time to change perspectives, priorities, entire worldviews. This is what first contact with another civilization would actually look like if that civilization existed at Proxima Centauri, our closest possible interstellar neighbour. Not a conversation, not an exchange, just messages sent into the void, taking years to arrive, receiving responses years later, each side always responding to old information, always operating on outdated assumptions, never able to achieve any kind of real-time interaction. And this is the best case scenario. This is the closest star. Every other star in the galaxy is farther away, which means every other potential civilization, every other possible point of contact would have even longer communication delays. Barnard's star at 6 light-years would have a 12-year round-trip communication time. Sirius at 8.6 light-years would be 17.2 years. Vega at 25 light-years would be 50 years. You could send a message to Vega as a young adult and receive a response when you're elderly, if you lived long enough. But let's set aside the question of communication and think about something more fundamental. Think about what 4.24 light-years of empty space actually contains. Nothing. Mostly nothing. Near-perfect vacuum. The occasional atom of hydrogen. Trace amounts of dust. Cosmic rays. The faint background glow of the universe itself. But in terms of matter, in terms of stuff, there's almost nothing there. The space between our Sun and Proxima Centauri is emptier than any vacuum we can create on Earth. It's empty in a way that's hard to truly comprehend. If you were somehow floating in the middle of that space, exactly halfway between the Sun and Proxima Centauri, both stars would look like bright points of light in the sky. Neither would look like a disk. Neither would look close. You would be surrounded by darkness and stars with no nearby objects, no planets, no asteroids, no comets. Nothing but emptiness in every direction. The nearest solid ground would be more than 2 light-years away in any direction. You would be more isolated, more alone, than any human has ever been or ever could be, while remaining in the solar system, and that emptiness extends in all directions. Proxima Centauri isn't special, it's not uniquely close. It just happens to be the nearest star to us, but the next nearest star is also several light-years away. Every star in our region of the galaxy is separated from every other star by light-years of empty space. This is normal. This is the default structure of the universe. Stars are not clustered together. They're scattered through space with vast distances between them, distances so large that even light takes years to cross them. Our galaxy, the Milky Way, contains somewhere between 100 and 400 billion stars. That's an enormous number, an almost incomprehensible number. But those stars are spread across a disk about 100,000 light-years in diameter. If you do the math, if you calculate the average distance between stars, you find that most stars are several light-years apart from their neighbours. Some are closer, some are much farther. But the typical separation is measured in light-years, plural, multiple years of light travel time between one star and the next. This means the Milky Way, despite containing hundreds of billions of stars, is mostly empty space. The volume between stars is vastly larger than the volume occupied by stars themselves. If you could somehow travel through the galaxy at random, You would spend almost all your time in the dark, in the emptiness, in the regions where stars are visible only as distant points of light. You would only rarely pass close to a star. The galaxy is not a dense collection of stars. It's a sparse scattering of stars through an immense volume of mostly nothing. And Proxima Centauri, at 4.24 light-years away, represents one of the smaller gaps. It's our nearest neighbour, which means most stars are farther away than this. Most stars are separated by distances that light takes 5, 10, 20, 50 years to cross. The isolation we're describing, the temporal disconnection, the impossibility of real-time interaction, is not unique to our relationship with Proxima Centauri. It's the normal state of affairs for stars in the galaxy. Every star exists in its own temporal bubble, separated from every other star by years of light travel time, unable to share a present moment with anything except the planets and objects immediately orbiting it. This is what interstellar distance does. It fragments the galaxy into isolated islands of present time, each one centered on a star, each one extending only as far as light can travel quickly enough for delays to remain small. Our island includes the Sun, the planets, the moons, the asteroids, the comets, everything gravitationally bound to our star, but it doesn't include Proxima Centauri. That star exists in its own island, its own temporal zone, forever 4.24 years out of sync with us. And the farther you look, the more islands you see. Each star, each system, each point of a light in the sky is its own separate entity, existing in its own version of now, isolated from every other star by the fundamental speed limit of information. Light tries to bridge these gaps. Light carries information from one island to another, but even light takes years to make the journey, and by the time it arrives, the information is old. The present moment has already moved on. This is why a light year matters, not just as a unit of measurement, but as a representation of isolation. 1 light year is the distance that creates a 1-year delay in information. It's the distance that separates one present moment from another by an entire year. And when stars are separated by multiple light years, they're separated by multiple years of temporal disconnection. They exist in parallel but never together, never sharing the same now, never experiencing the universe simultaneously. And we're still only talking about nearby stars. We're still discussing our immediate stellar neighbourhood, the stars within a few light years, the ones we can see individually, the ones we can study in detail. What happens when we expand our view further? What happens when we look not at individual stars but at the structure those stars form across larger scales? The Milky Way galaxy is a barred spiral galaxy containing somewhere between 100 and 400 billion stars. It's shaped like a disk with spiral arms curving out from a central bar-shaped structure, and the entire thing rotates slowly around a supermassive black hole at its centre. Our Sun is located about 26,000 light-years from that galactic centre, roughly halfway out from the core to the edge, in a minor spiral arm called the Orion Spur. When you look up at the night sky and see the band of light stretching across the darkness, that cloudy river of stars, you're seeing the Milky Way from the inside looking edge-on through the disk, 26,000 light-years to the galactic centre. Let's pause on that number. Light from the centre of our galaxy takes 26,000 years to reach Earth. The light you would see if you pointed a telescope toward the galactic core left that region 26,000 years ago. Humans didn't have written language 26,000 years ago. We didn't have cities. We didn't have agriculture. We were still living in small hunter-gatherer groups, making stone tools, painting on cave walls. The light reaching us now from the galactic centre began its journey before human civilization existed in any form we would recognise. This means when you observe the galactic centre, you're not seeing it as it is today. You're seeing it as it was 26,000 years in the past. If the supermassive black hole at the centre consumed a star yesterday, we won't see that event for another 26,000 years. If something catastrophic happened at the core right now, some massive release of energy, some dramatic change in the structure of the galactic centre, we wouldn't know until the year 28,024. Our entire civilization could rise and fall multiple times before the light from that event reaches Earth. And it's not just the centre. The Milky Way is about 100,000 light-years in diameter. If you wanted to send a light signal from one edge of the galaxy to the opposite edge, it would take 100,000 years for that signal to arrive. 100,000 years. That's longer than anatomically modern humans have existed as a species. That's longer than the entire history of Homo sapiens on Earth. A signal sent from the far side of the galaxy when the first modern humans were just beginning to migrate out of Africa would only now be reaching the opposite edge. Think about what this means. The Milky Way, our home galaxy, the structure that contains our Sun, and all the stars we can see with our naked eyes, is so large that light takes 100,000 years to cross it. This is not empty space between galaxies. This is not the void between separate structures. This is within a single galaxy. One continuous collection of stars, all gravitationally bound to the same system, all orbiting the same central mass, and yet so spread out, so vast in scale, that light requires 100,000 years to travel from one side to the other. The Milky Way does not exist in a single moment. It cannot. The information that would allow it to exist in a single moment, the light that would need to travel from every part of the galaxy to every other part simultaneously, would require 100,000 years to propagate. Different regions of the galaxy are experiencing different moments in time, separated by tens of thousands of years of light travel delay. The galactic center exists in one temporal state, the outer edges exist in another, the region where our Sun is located exists in yet another, and none of these regions share a present moment. When we look at a star on the opposite side of the galaxy, we're not seeing it as it is now. We're seeing it as it was tens of thousands of years ago. That star might not even exist anymore. It might have gone supernova. It might have been consumed by a black hole. It might have been gravitationally ejected from the galaxy entirely. We have no way of knowing. The light we see is old light, ancient light, light that began its journey before human civilization, before agriculture, before written history. The star we're observing is a ghost, an image of something that was real once but may not be real anymore. And this applies to every star we can see. Every single point of light in the night sky is a view into the past. The farther away the star, the deeper into the past we're looking. Proxima Centauri shows us 4.24 years ago. Sirius shows us 8.6 years ago. Deneb, a bright star in the constellation Cygnus, shows us about 2,600 years ago. That light left Deneb when ancient Greece was just beginning to emerge as a civilization. When that light began its journey, Socrates wouldn't be born for another 200 years. The light travelled through space while empires rose and fell on Earth, while languages were invented and forgotten, while entire cultures came into existence and disappeared, and it only just arrived here, now, for us to see. The galaxy is not a static thing. It's not a snapshot. It's a collection of images from different times, all layered on top of each other. When you look at the Milky Way stretched across the night sky, you're seeing thousands of years of history simultaneously. Stars that are relatively close show you the recent past. Stars that are far away show you the distant past. The entire thing is a temporal composite, a patchwork of different moments in time, unified only by the fact that the light from all those moments happens to be reaching Earth right now. This is why astronomers often say that looking out into space is looking back in time. It's not a metaphor, it's literally true. The farther you look, the farther back in time you see. Distance and time are not separate things in astronomy. They're the same thing. A star that's 10,000 light years away is a star you're seeing as it was 10,000 years ago. A star that's 50,000 light years away is a star you're seeing as it was 50,000 years ago. Distance equals time, always, without exception. Now let's think about what this means for our understanding of the galaxy's structure. When astronomers create maps of the Milky Way, when they show you images of the spiral arms and the central bar and the distribution of stars, those maps are not showing you the galaxy as it exists right now. They're showing you a reconstruction, a best guess about what the galaxy might look like if you could somehow see all of it at the same instant. But that's impossible. You can't see the whole galaxy at the same instant because the light from different parts of the galaxy takes different amounts of time to reach you. The map is built from observations made over years or decades. Observations of stars at different distances, stars whose light left them at different times. A star 1,000 light years away contributes light from 1,000 years ago. A star 50,000 light years away contributes light from 50,000 years ago. The map stitches together these different times into a single image, but the image doesn't represent a single moment. It represents a span of time, a range of moments, all compressed into what looks like simultaneity but isn't. And the galaxy is changing during this time. Stars are being born, stars are dying, stars are moving through space, orbiting the galactic center, shifting position relative to each other. The spiral arms are rotating, the structure is evolving, nothing is static. But we can't see these changes in real time because the light travel delays are too large. We're always watching the past, always observing events that finished thousands of years ago. The galaxy we study is a historical galaxy, a galaxy that existed in the past, and the farther out we look, the deeper into that past we see. This creates a strange situation for understanding galactic events. Supernovae, for example. When a massive star explodes, it releases an enormous amount of energy in a very short period of time. The explosion is visible across vast distances. For a few weeks, the supernova can outshine entire galaxies, but when we observe a supernova in our galaxy, we're not seeing it happen now. We're seeing it happen in the past, sometimes the distant past. The supernova that created the Crab Nebula, one of the most studied objects in astronomy, was observed by Chinese astronomers in the year 1054. They recorded a guest star that appeared in the sky, bright enough to be visible during the day for several weeks, but that star didn't explode in 1054. It exploded about 6,500 years earlier. The light from the explosion took 6,500 years to reach Earth. When the Chinese astronomers saw the supernova, the actual explosion had already been over for more than 6 millennia. The star was already gone. What they were seeing was ancient light, photons that had been travelling through space since long before human civilization began, and this happens with every astronomical event, every gamma-ray burst, every stellar collision, every black hole merger. Everything we observe in the galaxy is something that happened in the past. The more distant the event, the older it is. We're not watching the universe unfold in real time. We're watching a recording, a replay, a historical document written in light. The Milky Way contains 100 to 400 billion of these historical records. Each star is a separate timeline, a separate moment frozen in the light that's travelling toward us. Some of those moments are recent from just a few years ago, some are ancient from tens of thousands of years ago, and they all exist simultaneously in our observation. When you look up at the night sky, you're seeing a gallery of the past, a museum of moments, each one representing a different slice of history, all of them arriving at your eyes at the same time but originating from vastly different points in the timeline. This is the structure of the galaxy. Not just a spatial structure, but a temporal one. Not just a collection of stars arranged in space, but a collection of moments arranged in time, layered according to distance, creating a three-dimensional map where the third dimension is not just depth, but history. The farther away something is, the older it is. Distance and age become interchangeable. Light years measure both how far and how long ago. And the Milky Way, vast as it is, 100,000 light years across, containing hundreds of billions of stars, is just one galaxy among trillions. It's not special, it's not unusually large, it's an average spiral galaxy in an average region of space. There are bigger galaxies, there are smaller galaxies, there are galaxies with different shapes, different structures, different numbers of stars, and all of them, every single one, exists in this same state of temporal fragmentation, where different parts exist in different moments, separated by light travel time, unable to share a present. But we haven't left the Milky Way yet. We've only measured its internal distances. What happens when we look beyond? What happens when we point our telescopes not at stars within our galaxy, but at other galaxies entirely? What happens when we try to measure the distances not just across our local structure, but across the universe itself? The Andromeda Galaxy is the nearest large galaxy to the Milky Way. It's a spiral galaxy, similar in structure to our own, containing roughly 1 trillion stars. On a clear, dark night, far from city lights, you can see it with your naked eye as a faint fuzzy patch in the constellation Andromeda. It doesn't look like much, just a small smudge against the darkness, but that smudge is an entire galaxy, 1 trillion stars, hundreds of billions of planets, unfathomable amounts of matter and energy and space, all compressed into a tiny spot of light in our sky. Andromeda is approximately 2.5 million light-years away from us. This means the light you see when you look at Andromeda left that galaxy 2.5 million years ago, not 2.5 thousand years, 2.5 million years. The light began its journey before modern humans existed, before Homo sapiens evolved, The light was already travelling through space when our ancestors were still Australopithecus, early hominids living in Africa, not yet walking fully upright, not yet using sophisticated tools, not yet anything we would recognise as human. That light travelled through the void for 2.5 million years. It crossed the space between galaxies, moving at 186,000 miles per second, never slowing, never stopping, always moving forward. While that light was travelling, evolution continued on Earth. Species emerged and went extinct. Ice ages came and went. The climate changed, continents shifted, and eventually, after millions of years of evolution, a species arose that could build telescopes and point them at the sky and see that ancient light and understand, at least partially, what it meant. When you look at Andromeda, you're not seeing the galaxy as it is today. You're seeing it as it was 2.5 million years in the past. The stars you observe have already changed. Some have gone supernova, some have been born. The structure of the galaxy has shifted slightly. Everything you see is outdated by millions of years. The Andromeda you're looking at is a ghost, an image of something that doesn't exist anymore in the form you're seeing it. The real Andromeda, the one existing right now in this moment, is unknowable to us. We won't see what it looks like today for another 2.5 million years. Andromeda is close. By cosmic standards, by the scale of the universe, Andromeda is our nearest neighbour. It's part of what astronomers call the local group, a small cluster of galaxies that includes the Milky Way, Andromeda, and about 50 smaller galaxies all gravitationally bound together. This is our immediate cosmic neighbourhood, and even within this neighbourhood, even among galaxies that are relatively close to each other, the distances are measured in millions of light years. The Triangulum Galaxy, another member of the local group, is about 3 million light years away. When you observe it, you're seeing it as it was 3 million years ago. The light is older than the genus Homo. It's older than stone tools. It predates everything we think of as distinctly human. Other galaxies in the local group are farther still. Some are 4 or 5 million light years away. The light from those galaxies is so old that when it began its journey, Earth's climate and geography were fundamentally different from what they are now. But the local group is tiny. It's just a small collection of galaxies occupying a region of space about 10 million light years across. Beyond the local group, the distances explode. The nearest large cluster of galaxies to us is the Virgo cluster, which contains somewhere around 1,300 galaxies. It's located about 65 million light years away. When you look at galaxies in the Virgo cluster, you're seeing them as they were 65 million years ago. That's when the light left them. 65 million years ago, dinosaurs still walked on Earth. The asteroid that would cause their extinction had just struck the planet. The light from the Virgo cluster began travelling toward us at the same moment that the Cretaceous period was ending and the age of mammals was beginning. That light has been travelling ever since. It moved through empty space while dinosaurs went extinct, while mammals diversified, while continents drifted apart, while ice ages came and went, while primates evolved, while humans emerged and spread across the planet and built civilizations and invented language and mathematics and science and astronomy. The entire history of human existence, from the first hominids to the present day, happened while that light was in transit, and it only just arrived, right now, for us to see. This is what extragalactic distances mean. They're not just measurements of space, they're measurements of time on scales that dwarf human history. When you observe distant galaxies, you're not looking across space, you're looking across time, deep time, geological time, evolutionary time. Time spans so vast that they make human lifespans and human civilizations seem like brief flickers. And we're still talking about relatively nearby galaxies. The Virgo cluster is part of an even larger structure called the Virgo supercluster, which contains dozens of galaxy clusters and spans about 110 million light years. Our local group is a tiny component at the edge of this supercluster. We're looking at the rest of it as it was 110 million years ago, back in the mid-Cretaceous period, when flowering plants were just beginning to diversify, when the continents were still connected in different configurations, when Earth's ecosystem was completely alien to what exists now. But even superclusters are small structures compared to the full scale of the observable universe. Beyond our supercluster, there are thousands of other superclusters, each containing thousands of galaxies, each separated from the others by hundreds of millions of light years. The Coma cluster is about 320 million light years away. The light we see from it began travelling toward us in the Carboniferous period, when the first reptiles were just evolving, when insects were enormous, when Earth's forests were creating the coal deposits we mine today. The farther out we look, the older the light becomes. Galaxies at 1 billion light years show us the universe as it was 1 billion years ago. Galaxies at 5 billion light years show us the universe from before the Sun existed. The light from those galaxies began travelling before our solar system formed, before Earth existed, before any of the planets or moons or asteroids in our neighbourhood came into being. That light has been travelling for longer than our planet has existed, and we can see even farther. With powerful telescopes, with long exposure times, with careful observations, we can detect galaxies that are 10 billion light years away, 12 billion light years, 13 billion light years. The most distant galaxies ever observed are so far away that their light has been travelling for more than 13 billion years. That light began its journey less than 1 billion years after the Big Bang, when the universe itself was young, when the first galaxies were just beginning to form, when the cosmos looked nothing like it does today. This is the observable universe, the sphere of space around us from which light has had time to reach Earth since the beginning of the universe. It extends roughly 46 billion light years in every direction, creating a sphere about 93 billion light years in diameter. This isn't because the universe is only 93 billion light years across. The universe might be infinite, we don't know. But the observable universe is limited by the speed of light and the age of the universe. Light from anything farther than about 46 billion light years away hasn't had time to reach us yet. It's still travelling, still crossing the immense distances of space, and it might never reach us because the expansion of space is carrying those distant regions away faster than light can travel through that expanding space. The edge of the observable universe is not a physical boundary, it's a temporal boundary. It's the limit of how far back in time we can see. When we look at the most distant galaxies, we're seeing the universe as it was more than 13 billion years ago. We're seeing the early universe, the young universe, a cosmos that was smaller, denser, hotter, more uniform, a universe without the structure we see today, without the vast cosmic web of galaxy clusters and superclusters and voids. Everything we observe in the universe is a view into the past. The farther we look, the deeper into that past we see. There is no way to observe the present state of distant objects because the information about their present state hasn't reached us yet. It's still travelling, still moving through space at light speed, still years or centuries or millions or billions of years away from arrival. We're trapped in our local present, surrounded by an expanding shell of history, with the oldest history at the farthest distances and the most recent history close to home. This creates a strange picture of the cosmos. When astronomers make maps of the universe, when they show the distribution of galaxies across space, those maps are not showing you the universe as it is now. They're showing you different eras of the universe, all layered together. Nearby galaxies show you the relatively recent past from millions of years ago. Distant galaxies show you the deep past from billions of years ago. The map is a timeline stretched across space, with time encoded as distance. The universe we observe is not the universe that exists. It's the universe that existed, at various points in history, all brought together in our present moment by the light that's been travelling toward us for different amounts of time. We are observers of history, not of the present. We are watching a recording of events that finished long ago, some of them so long ago that the objects we're observing might not even exist anymore. They might have changed, evolved, merged with other galaxies, been torn apart by gravitational interactions. We have no way of knowing because the light that would tell us what happened is still in transit, still years or millennia or eons away from reaching us. And this brings us to the fundamental limitation of observation. We cannot see the universe as it is. We can only see it as it was, and the farther we look, the older the version we see. Distance equals time, always, without exception. A light year is not just a measurement of space, it's a measurement of history. There is no such thing as seeing something as it is right now, not in astronomy, not when you're looking at anything beyond Earth. Even the moon, barely a second away at light speed, shows you a past version of itself. The sun shows you a version from 8 minutes ago. The nearest stars show you versions from years ago. Distant galaxies show you versions from millions or billions of years ago. Every single observation is an observation of the past. The present moment, The actual state of the universe as it exists right now is completely inaccessible to us. This isn't a technological limitation. It's not something we can fix with better instruments or more powerful telescopes or more sophisticated detection methods. It's fundamental physics. Information travels at the speed of light. Light takes time to cross distances. Therefore, by the time information about a distant object reaches us, that object has already changed. It has already moved forward in time. What we're seeing is a record of what it was, not what it is. Think about what this means. When you look at Andromeda, 2.5 million light years away, you're seeing it as it was 2.5 million years ago. The galaxy has continued existing during those 2.5 million years. Stars have been born and died. Planets have formed. The structure has evolved. But none of that is visible to you. The light carrying information about those changes hasn't reached Earth yet. It's still in transit. It will arrive millions of years from now, long after you're gone, long after human civilization as we know it has ended. The Andromeda you see, and the Andromeda that exists, are separated by 2.5 million years of history that you cannot observe. Now multiply this across the entire observable universe. Every galaxy you can see is showing you a different moment in cosmic history. Close galaxies show you the recent past. Distant galaxies show you the ancient past. The most distant galaxies show you the early universe, the way it looked more than 13 billion years ago when it was young and hot and still forming its first large-scale structures. All of these different moments exist simultaneously in our observation. We see them all at once, layered on top of each other, creating a composite image of cosmic history. But here's the strange part. While we're looking backward at those distant galaxies, seeing them as they were billions of years ago, observers in those galaxies, if any exist, are looking backward at us. They're seeing the Milky Way as it was billions of years ago. They're seeing our galaxy before the sun formed, before Earth existed, before life began. They're watching our past while we watch theirs, and neither of us can see the other as we actually are right now. This creates a fundamental asymmetry in the universe. There is no shared present moment between distant objects. Each object exists in its own local now, surrounded by a sphere of observable past. The farther away something is, the deeper into its past we see, and this relationship is reciprocal. Distance creates temporal disconnection in both directions. We see their past, they see our past. The present remains forever hidden behind the light travel time, and it's not just that we see the past, it's that the past is all we can ever see. There is no method, no technique, no future technology that will allow us to observe distant objects as they exist right now. We could build perfect telescopes. We could eliminate all sources of distortion and interference. We could collect every single photon travelling toward us. And we would still be looking at the past because those photons left their source in the past. They've been travelling for years or millennia or eons, and by the time they reach us, they're carrying old information. This means the universe has a kind of built-in delay, a lag between reality and observation, an unavoidable gap between what is and what we can know. And this gap grows with distance. Look 1 light year away and you see 1 year into the past. Look 10 light years away and you see 10 years into the past. Look 1 billion light years away and you see 1 billion years into the past. The relationship is direct and unchangeable. Distance equals time. Always. Let's think about the implications for understanding the universe. When astronomers study galaxy formation, they observe galaxies at different distances. Nearby galaxies show them relatively mature systems, galaxies that have had billions of years to develop, to form stars, to create heavy elements, to settle into stable structures. Distant galaxies show them younger systems, galaxies that formed more recently in cosmic history, galaxies that are still active and chaotic and rapidly evolving. By comparing galaxies at different distances, astronomers can piece together a timeline of how galaxies evolve over cosmic time. But this timeline is not constructed by watching individual galaxies change. It's constructed by looking at different galaxies at different stages of development, stages that are separated by billions of years and billions of light years. The nearby galaxy showing a mature state and the distant galaxy showing a young state are not the same object at different times. They're different objects, observed at different points in cosmic history, assumed to be representative of a general evolutionary process. The actual evolution of any individual galaxy, the changes it undergoes over billions of years, is completely invisible to us because we can't watch it happen in real time. We can only see single, frozen moments from each galaxy. moments separated by the time it takes light to travel. The same principle applies to everything else in astronomy: stellar evolution. The formation of planetary systems, the growth of supermassive black holes, the expansion of the universe itself. Everything we know about cosmic change comes from comparing different objects at different distances, which means different moments in time, and inferring how things evolve by looking at those different moments. We're reconstructing a movie from individual frames scattered across billions of years of history, and some of those frames show us things that no longer exist. Galaxies we observe at 10 billion light-years might have merged with other galaxies by now. Stars we see in distant galaxies might have gone supernova. Planets might have formed, and life might have emerged, and entire civilizations might have risen and fallen. And we have no way of knowing because the light carrying that information is still in transit. It hasn't reached us. It won't reach us for billions of years. And by the time it does, if we're still here to see it, we'll be observing events that concluded billions of years in our past. This is the fundamental nature of astronomical observation. It's archaeology. It's the study of ancient light that carries information about events and objects that are long gone by the time we see them. The universe we study is a historical universe, a universe of the past, and the deeper we look, the farther back in time we go, the more ancient and alien the universe becomes. There's also something profoundly isolating about this. We're trapped in our local present, unable to see or interact with the present state of anything beyond our immediate vicinity. The sun is 8 minutes out of reach. The nearest stars are years out of reach. Nearby galaxies are millions of years out of reach. Distant galaxies are billions of years out of reach. We are surrounded by history, by light from the past, by information about things that used to be but might not be anymore. And if there are other civilizations out there, other intelligent species looking up at their own night skies, they're experiencing the same isolation. They're seeing their own version of the past. They're observing galaxies and stars that no longer exist in the forms they're seeing. They might be looking at the Milky Way right now, seeing it as it was millions or billions of years ago, observing our galaxy before humans existed, maybe even before Earth existed. And we have no way of communicating with them in any meaningful time frame, because the distances are too vast and light is too slow. If we sent a message to a galaxy 1 billion light-years away, it would take 1 billion years for that message to arrive. If they responded immediately, their response would take another 1 billion years to get back to us. 2 billion years for a round-trip communication. The species that sent the message and the species that received the response would be separated by evolutionary timescales. They wouldn't even be the same species anymore. Entire branches of evolution could unfold in the time it takes for a single exchange of information. This is what light years measure. Not just distance, but isolation. Not just space, but separation. Not just how far something is, but how disconnected we are from it. A light year is a unit of unreachability, a measurement of how thoroughly we're cut off from the rest of the universe by the fundamental speed limit of information and the vastness of cosmic distances. And yet, despite this isolation, we can still observe. We can still collect the ancient light and analyze it and learn from it. We can reconstruct the history of the universe, even though we can't see its present. We can understand how galaxies form and evolve even though we can't watch individual galaxies change. We can map the large-scale structure of the cosmos, even though that map shows us different eras stitched together, rather than a single moment. Light carries information across vast distances and vast timescales, and even if that information is old by the time it reaches us, it's still valuable. It still tells us something real about how the universe works. But it also reminds us of our limitations. We are observers of the past, not the present. We are historians, not journalists. We study what was, not what is, and the farther we look, the older the history becomes, until we're looking at light from the very beginning of the universe itself, light that's been travelling for more than 13 billion years, light that shows us a cosmos so different from what exists now that it's almost unrecognisable. This is the reality of cosmic distance. Every light year is a year into the past. Every million light years is a million years into the past. Distance and time are the same thing. You cannot separate them, and this means the universe we observe is always, inevitably, fundamentally a universe of history. The present remains forever out of reach, hidden behind the speed of light and the vastness of space. There's a question that might have occurred to you by now. If cosmic distances are so vast, so incomprehensibly large, why do we use light years at all? Why not just stick with miles or kilometers? Why invent a new unit when we already have perfectly good ways of measuring distance? The answer is simple, but it reveals something fundamental about human cognition and the limits of our intuition. Miles don't work for cosmic distances, not because the math is wrong, but because the numbers become meaningless. The nearest star, Proxima Centauri, is about 25 trillion miles away. That's 25 followed by 12 zeros. The number is so large that it stops connecting to anything in human experience. You have no reference point for 25 trillion. You can't visualize it. You can't break it down into smaller units that make sense. It's just a very large number, abstract and disconnected from anything tangible. Andromeda is about 15 quintillion miles away. That's 15 followed by 18 zeros. The edge of the observable universe is roughly 550 sextillion miles away. These numbers are technically accurate. They describe real distances, but they don't help you understand those distances. They don't give you any intuition about what those distances mean or how they relate to each other or why they matter. They're just increasingly large numbers that all blur together into very, very far. This is the problem with using human-scale units for cosmic-scale distances. The units were designed for measuring things within human experience. Miles work well for measuring the distance between cities. They work reasonably well for measuring the distance across continents or around the Earth. They even work, barely, for measuring distances within the solar system, though the numbers start to get awkward. But once you leave the solar system, once you try to measure interstellar or intergalactic distances in miles, the system breaks down completely. The numbers become so large that they lose all meaning. So we needed something else. We needed a unit that could handle cosmic distances without producing incomprehensibly large numbers. We needed a way to measure things that were fundamentally beyond human scale, using something that's still connected to human understanding, at least partially. And the solution was to stop measuring distance directly and start measuring the time it takes light to travel. A light year is the distance light travels in 1 year. It's approximately 5.88 trillion miles, or about 9.46 trillion kilometers. But you don't need to remember those conversions. That's the whole point. You don't think about a light year as 5.88 trillion miles. You think about it as 1 year of light travel. This changes the entire framework of understanding. Instead of asking, how many miles away is that star? You ask, how long does it take light to get there? And the answer, 4 light years or 10 light years or 1,000 light years, tells you something immediate and meaningful. It tells you that you're looking into the past. 4 light years means you're seeing 4 years ago. 10 light years means you're seeing 10 years ago. 1,000 light years means you're seeing 1,000 years ago. The unit of distance automatically converts to a unit of time, and time is something we understand. We know what a year feels like. We know what 10 years feels like. We can imagine 1,000 years even if we can't experience it directly. The light year bridges the gap between incomprehensible spatial distances and comprehensible temporal durations. But there's something deeper happening here. The light year is not just a convenient unit. It's an acknowledgement that our traditional ways of thinking about distance don't apply to the universe. When you measure something in miles, you're implicitly assuming that the distance is something you could, at least theoretically, traverse. You could walk a mile. You could drive 100 miles. You could even imagine, in some abstract way, travelling 1,000,000 miles if you had enough time and the right vehicle. The unit implies crossability. It implies that distance is something to be overcome through motion. But cosmic distances are not crossable, not in any meaningful human time frame. You cannot travel to another star with current technology. You cannot visit another galaxy. The distances are too vast and the speeds required are too high. Even if we developed spacecraft that could travel at significant fractions of light speed, which is far beyond our current capabilities, the journeys would take lifetimes or generations or millennia. Measuring these distances in miles suggests a kind of accessibility that doesn't exist. It suggests that the distance is just a very long version of distances we're familiar with, when in fact it's something qualitatively different. The light year acknowledges this difference. It stops pretending that cosmic distances are just larger versions of terrestrial distances. Instead, it measures them in terms of the only thing that can actually cross them at meaningful timescales, light itself. And because light is the fastest thing that can exist, because nothing with mass can ever reach light speed, Measuring distance in light years is also measuring the absolute minimum time it would take for information or influence to travel between 2 points. If something is 1 light year away, it takes at least 1 year for anything to get there from here or to get here from there. Not 1 year if you travel really fast. 1 year at the absolute cosmic speed limit. 1 year under ideal, impossible conditions. In reality, anything travelling at less than light speed would take longer, much longer. Voyager 1, travelling at 0.006% of light speed, would take over 17,000 years to cover 1 light year. A human spacecraft with more realistic speeds might take tens of thousands or hundreds of thousands of years. So the light year is actually measuring isolation. It's measuring the minimum amount of time that separates one point in space from another. It's measuring how long you have to wait for light to arrive, for information to propagate, for any kind of causal influence to travel from one place to another. 1 light year equals 1 year of isolation. 10 light years equals 10 years of isolation. 1,000,000 light years equals 1,000,000 years of isolation. The unit quantifies disconnection, and this is why the light year feels more honest than miles or kilometers when dealing with cosmic distances. It doesn't pretend that the distance is something you could cross with enough effort or time. It acknowledges that the distance creates a temporal barrier, a delay, a fundamental separation between events and observations. It builds the speed of light, the cosmic speed limit, directly into the measurement, reminding you constantly that there's a limit to how fast information can travel and that this limit matters enormously when distances are large. There's also something elegant about using light itself as the measuring stick. Light is universal. It travels at the same speed everywhere in the universe, in all reference frames, under all conditions. The speed of light is a fundamental constant of physics, one of the few numbers that never changes no matter where you are or what you're doing. By tying our distance measurements to light, we're tying them to something absolute and unchanging. A light year is the same distance whether you're on Earth or in another galaxy. It doesn't depend on local conditions or arbitrary human choices. It's grounded in the fundamental structure of space-time itself. And light is what we observe. When we look at distant objects, we're literally seeing light that travelled from those objects to us. The light is the medium of observation. It makes sense to measure distances in terms of how long that medium takes to travel. When you say a star is 10 light years away, you're saying that the light you're seeing from that star right now left the star 10 years ago. The measurement directly describes the observational relationship. But the light year also reveals something uncomfortable. It reveals that the universe is structured in a way that makes simultaneity impossible across large distances. There is no universal now. There's only local now, surrounded by expanding shells of past. The farther away something is, measured in light years, the farther into the past you're seeing it. The unit itself encodes temporal disconnection. Every light year of distance is also a year of delay, a year of separation, a year of unbridgeable gap between event and observation. This is why we invented the light year, not just because the numbers in miles get too large, though they do, but because miles measure the wrong thing. Miles measure a kind of distance that implies connection, accessibility, the possibility of travel. Light years measure the actual nature of cosmic distance, which is isolation, temporal delay, the fundamental impossibility of shared experience across vast scales. The light year is an admission that the universe doesn't work the way our intuition expects it to work. That distance at cosmic scales is not just more distance, it's something else entirely. Something that combines space and time into a single barrier that can't be overcome. We needed a unit that acknowledged this reality, a unit that stopped measuring space and started measuring the time-space barrier, a unit that made the isolation explicit rather than hiding it behind enormous numbers. And that unit is the light year, a measurement born from the collapse of human intuition when confronted with cosmic scale. There's something strange about being a species that can understand light years but cannot experience them. We can calculate the distance to Andromeda. We can measure the age of light from the early universe. We can map the structure of cosmic voids and superclusters spanning billions of light years. But we cannot feel those distances. We cannot travel them. We cannot even properly visualize them. They exist entirely outside the boundary of human sensory experience and human capability. A light year is approximately 5.88 trillion miles. You could write that number down. You could memorize it. You could use it in calculations. but you cannot truly comprehend it. Your brain did not evolve to process numbers of that magnitude. Evolution shaped human cognition to handle the distances relevant to survival, the distance to water, the distance to shelter, the distance a predator might cover before you need to run. These are human-scale distances, distances you can walk in minutes or hours or days. Everything in your brain's intuitive understanding of space is calibrated to this scale. When you try to extend that intuition to cosmic distances, it fails completely. You might think you understand that light year is very far. You might nod along when someone explains the numbers, but the understanding is intellectual, not intuitive. You don't feel the distance the way you feel the distance across a room or across your city. The visceral sense of space, the immediate awareness of how far something is, doesn't activate for cosmic distances. It can't. There's no evolutionary reason for it to exist. This creates a peculiar situation. Humans have extended their knowledge far beyond the limits of their intuition. We know about things we cannot directly sense. We understand phenomena that occur at scales vastly larger and vastly smaller than anything we evolved to perceive. We've built instruments that can detect individual photons from the edge of the observable universe. We've developed mathematics that can describe the curvature of space-time. We've constructed theories about the first fraction of a second after the Big Bang. And all of this knowledge exists in a realm completely disconnected from everyday human experience. You will never stand on Earth and feel how far away Proxima Centauri is. You will never look at Andromeda and viscerally sense the 2.5 million years of light travel time. You will never experience the emptiness of intergalactic space. These things are real. They exist. We have evidence for them. But they remain forever outside the boundary of what it means to be human at the most fundamental, embodied level. And yet, we are the species that discovered these distances. We are the ones who pointed telescopes at the sky and measured the parallax of nearby stars and calculated how far away they must be. We are the ones who noticed that galaxies are moving away from us and inferred that the universe is expanding. We are the ones who detected the cosmic microwave background radiation and determined that it's been travelling for more than 13 billion years. We discovered our own insignificance. We measured our own isolation. Think about what that means. Humans, living on a small planet orbiting an average star in an unremarkable galaxy, developed enough understanding of physics and mathematics and observation to determine that we are surrounded by distances so vast that light takes years or millennia or eons to cross them. We figured out that we're trapped in a tiny bubble of accessible space, that everything beyond our solar system is effectively unreachable, that the universe we observe is a museum of history rather than a window into the present. We learned that we are profoundly alone, separated from everything else by barriers we cannot cross and delays we cannot eliminate. This knowledge doesn't come with any practical benefit. Knowing that Andromeda is 2.5 million light years away doesn't help you survive. It doesn't help you find food or build shelter or raise children. It doesn't make your life easier or longer or happier. If anything, it makes existence feel smaller and more fragile. It reveals how limited we are, how confined to this one planet, how utterly incapable of reaching anything beyond our immediate cosmic neighbourhood. And yet we sought this knowledge anyway. We built observatories, we launched space telescopes, we dedicated careers and lifetimes to understanding the universe's structure and scale. We wanted to know, even though knowing would reveal our own insignificance. There's something almost defiant about that. Something that suggests that human curiosity transcends practical concerns. We don't just want to understand things that help us survive. We want to understand everything, even if it means confronting truths that are humbling or isolating or impossible to fully grasp. The light year encapsulates this strange human relationship with cosmic scale. It's a unit we invented to measure distances we can never cross, to quantify isolation we can never overcome, to describe a universe that operates on scales completely alien to our everyday experience. We created it because we needed some way to talk about these distances, some framework for organising our observations and calculations. But in creating it, we also codified our own limitations. Every light year is a reminder of how far we cannot go, how much we cannot reach, how thoroughly we are confined to our local pocket of space and time. If you could somehow travel at the speed of light, which you can't because you have mass and mass cannot reach light speed, you could circle the Earth 7.5 times in 1 second. You could reach the Moon in 1.28 seconds, You could reach the Sun in about 8 minutes, but it would still take you 4.24 years to reach Proxima Centauri. 4 years of continuous travel at the absolute cosmic speed limit just to reach the nearest star. And most stars are much farther away. Most of the galaxy is inaccessible even at light speed within a human lifetime, and other galaxies are utterly beyond reach, requiring millions or billions of years of travel even at the maximum possible velocity. This is the reality the light year describes, a reality where the universe is too large for human exploration, too spread out for human travel, too isolated for human connection across cosmic distances. We are bound to our planet and, at best, to our solar system. Everything else is observable but not reachable, knowable but not experienceable, real but forever distant. And there's a kind of loneliness in this understanding. Earth is the only place in the universe where you will ever stand. This solar system is the only one you will ever visit. The Sun is the only star you will ever see up close. Every other star is a point of light in the sky, separated from you by years or decades or centuries or millennia of light travel time. Every other galaxy is a distant smudge, millions or billions of light years away, existing in its own temporal island, completely disconnected from your present moment. You're here, now, on this planet, in this moment, and everything else in the universe is there, then, separated from you by distance and time, by light years of isolation, by the fundamental structure of space-time that prevents faster-than-light travel and ensures that information takes time to propagate. You cannot reach out and touch another star. You cannot visit another galaxy. You cannot even see them as they are right now. You can only see them as they were when the light that's arriving at your eyes began its long journey through the void. But you can understand this. You can know why it's true. You can measure the distances and calculate the delays and comprehend, at least intellectually, what it means to live in a universe structured this way. You invented the light year specifically to make this understanding possible. You created a unit that quantifies cosmic isolation so that you could talk about it, study it, incorporate it into your models of how reality works. This is the paradox of human understanding. We are small, confined, limited creatures living on a tiny rock in an incomprehensibly vast universe. And yet we are also the creatures who figured out how vast that universe is. We measured the distances that confine us. We calculated the barriers that isolate us. We invented units like the light year to describe our own unreachability from everything else that exists. The light year is not just a measurement, it's a statement about human limitation and human capability existing simultaneously. It acknowledges that we cannot cross cosmic distances while also demonstrating that we can understand them. It quantifies isolation while also showing that isolation can be studied, measured, incorporated into human knowledge. It's a unit born from the collision between what humans can know and what humans can do, between the vast scale of the universe and the tiny scale of human experience. And in that collision, in that gap between knowledge and experience, something emerges. Not conquest of the cosmos, not mastery of interstellar travel, but awareness, understanding. A species that knows where it is, how isolated it is, how small it is in the context of everything that exists. A species that can look up at the night sky and see not just points of light, but histories, distances, entire galaxies separated by eons of light travel time. A species that invented a unit specifically to measure its own cosmic loneliness, and then used that unit to map the structure of the universe itself. A light year is the distance light travels in 1 year. That's the simple definition, the one you probably knew before you started reading. It hasn't changed. The numbers haven't changed. Light still moves at 186,000 miles per second. A year is still a year. The nearest star is still 4.24 light years away. Andromeda is still 2.5 million light years distant. The edge of the observable universe is still roughly 46 billion light years from Earth. But perhaps what those numbers mean has changed. Perhaps you see them differently now, not just as measurements of distance, but as measurements of time. Not just as descriptions of how far away things are, but as descriptions of how disconnected we are from them. Not just as markers of space, but as barriers of isolation, temporal gaps that cannot be crossed, delays built into the fundamental structure of reality itself. When you look at the night sky now, you're not seeing the universe as it is. You're seeing it as it was: the moon from 1.28 seconds ago, the sun from 8 minutes ago, the nearest stars from years ago, distant galaxies from millions or billions of years ago. Every point of light is a window into history, and the farther away something is, the deeper into the past you're looking. Distance and time are the same thing out there. They cannot be separated. A light year measures both how far and how long ago. This is what the universe actually is. Not a collection of objects existing simultaneously in space, but a layered structure of different moments, different eras, different versions of reality, all reaching us at the same time but originating from vastly different points in cosmic history. The universe we observe is a patchwork of the past, stitched together by light that's been travelling for different amounts of time, creating the illusion of simultaneity when nothing we see is actually happening now. And we are small within this structure, confined to one planet, unable to travel to other stars, unable to see the present state of anything beyond our immediate vicinity, surrounded by light from the past, by information that is already old by the time it reaches us, by distances so vast that even light, the fastest thing that exists, takes years or millennia or eons to cross them. But we know this. We measured it. We understood it. We invented the light year specifically to describe it, to quantify it, to make it something we could study and discuss and incorporate into our understanding of how reality works. We are a species trapped in a tiny corner of an incomprehensibly large universe, and we know exactly how trapped we are. We calculated our own isolation. We measured our own insignificance, and perhaps that's enough. Not to conquer the cosmos, not to travel to distant galaxies, not to overcome the light-year barriers that separate us from everything else, but to understand, to know where we are, to recognize the structure we exist within, to see the universe not as we wish it were, but as it actually is: vast, old, isolated, beautiful in its scale and terrible in its emptiness, and knowable, at least partially, even from this small blue planet orbiting an average star. The light year is just a unit of measurement, but it's also a reminder of distance, of time, of limitation, of the gap between what we can know and what we can reach, of the universe's true nature, revealed through the simple fact that light takes time to travel and that time creates separation we cannot overcome. You already knew what a light year was, but now, perhaps, you understand what it means.